I want to start this video by emphasizing that when you have an integral from minus infinity to infinity of a function f of x dx, you have to split it up. You have to write it as an integral from minus infinity to some point in the middle. I like to pick 0, but you could pick a different point if you want. So integral minus infinity to 0 f of x dx plus the integral the rest of the way from 0 to infinity of f of x dx. And now each one of these integrals is defined in terms of a limit. The limit as t goes to minus infinity of the integral from t to 0 of f of x dx plus the limit as t goes to plus infinity of the integral from 0 to t of f of x dx. So why am I emphasizing this? Well, here's something you might think. Let's take the integral from minus infinity to infinity of x dx. And let's just say, well, I'm going to have a part that goes to minus infinity and a part that goes to plus infinity. So let me write the limit as t goes to plus infinity of the integral from minus t to t of x dx. And then, okay, this I know. This integral, well, if you think about what's going on, so here's a value of t, here's a value of minus t, and we're asking for the signed area under the graph of this function, and the negative area here cancels with the negative area here. Or said another way, this is an odd function, and we're taking an integral from minus t to t. So this is 0. So this is equal to the limit as t goes to infinity of 0. Because for any particular value of t, we're getting 0. So this should just be 0. Okay, why did I bring this up? This does not work. Even if you have an integral that starts at minus infinity and goes to plus infinity, do not think of it as an integral as t goes to infinity of a function from minus t to t. What really should happen here is that you write this as a limit as t goes to minus infinity of an integral from t to 0 of x dx plus a limit as t goes to infinity of integral 0 infinity x dx. We know here we get a limit as t goes, move this up a little bit, to minus infinity of 1/2 x squared evaluated at t and at 0 plus a limit as t goes to plus infinity of 1/2 x squared evaluated at, oh, sorry, this should be a t, at 0 and t. And here we get 0 minus infinity, and here we get infinity minus 0. These both diverge. Neither one of these limits converges to a number that's not plus or minus infinity. The first one goes to negative infinity, and the second one goes to positive infinity. So this whole integral diverges. The important property that we want is if you have an integral from negative infinity to infinity, and you split it up into two pieces, this whole integral converges if and only if both of the individual pieces converge. If either one of those pieces diverges, then the integral you started with diverges. So that's the important thing, and that's why we're really emphasizing that you have to split it up. When you split it up like this, if either one of these pieces diverges, then the whole thing diverges. In the rest of this video, I want to give an introduction to the second type of improper integral we'll think about. The first type was when we had a plus or minus infinity in the endpoints of our integral. And the second one are discontinuous integrals. That is, when the function we're trying to integrate is not continuous over the whole interval that we're integrating. So here's an example. Let's take an integral from 0 to 1 of natural log of x dx. And what's the problem here? Well, what does natural log look like? Natural log of 1 is 0, and then it goes off to infinity, but slowly. If you take natural log of a number, like natural log of 1 over e is -1, if you take a number between 0 and 1, you're getting something negative. But as you get closer and closer and closer to 0, you get something that gets more and more and more negative. Natural log of 0 is not defined. We have this vertical asymptote to this function that as x goes to 0 from the plus direction, natural log of x goes to -infinity. So the problem is the function is not defined at the bottom endpoint. So like we did in the first part, how are we going to fix this? We're going to define this integral in terms of a limit. And natural log is continuous between t and 1 when t is a positive real number. So we're going to say what happens when we take the integral from t to 1 of ln of x dx, where t is a positive real number, but is getting smaller and smaller and smaller and smaller. So we're taking a limit as t goes to 0 from the plus direction of the integral from t to 1 of ln of x dx. But this integral we know how to do. This has nothing to do with the limit. The limit will just keep around and do this integral like we would have before. So remember, this is one of those ones that we did by integration by parts. And what we got was x ln of x minus x. And we have to evaluate at t and at 1. So we get is the limit as t goes to 0 from the plus direction of 1 times natural log of 1 minus 1 minus t times natural log of t minus t. Okay, so this whole thing should be inside parentheses. Natural log of 1 is 0, so this part is 0. What we're getting is something going to -1. So we have the limit as t goes to 0 from the plus direction of -1 minus t times natural log of t. And then this minus t is a plus t, but t is going to 0, so that goes to 0. So the key question is just, what is the limit as t goes to 0 from the plus direction of minus t times natural log of t? So natural log of t we said is going to -infinity, but t is going to 0. And again, the trick is to think of this limit in a slightly different way and then apply L'Hopital's rule. So we can think of this as natural log of t divided by -1 over t. Right? -1 over t is negative t, but now the numerator is going to -infinity and the denominator is going to -infinity. So we have this infinity over infinity limit. So the thing to do is apply L'Hopital. L'Hopital's rule says that this is the limit as t goes to 0 from the plus direction of the ratio of their derivatives. So we'll take ln of t plus over minus t to the -1, sorry, not plus, derivative. And what we get is a limit as t goes to 0 from the plus direction of 1 over t divided by -1 minus 1. We get 1 over t squared. Right, we get a t to the -2, and the minuses cancel. So the point is, this is just, now this t squared comes up to the top. We just get a limit as t goes to 0 from the plus direction of t, which is 0. And so what we see is that this limit that we were trying to figure out is -1 minus 0 is just -1. So what does that mean? This whole integral, we first saw that it was continuous everywhere except the bottom endpoint. So we defined it as a limit as t approached the bottom endpoint from the direction of the top endpoint. We then did this integral like before, and we had to compute a limit using L'Hopital's rule. But in the end, that limit exists, and we get a finite number. So this integral is convergent and equal to -1.